So this is accelerating upwards because this is lighter than this weight, and this one is accelerating downwards over here because of the pulley. Right? Even though they're both moving almost in the same fashion along this whole pulley system. We'll label it like this. So then now for this mass, Ft is upwards, mg is downwards again, and then we take into account the pulley by making the acceleration negative. Okay. Now we can let's calculate the acceleration. So we say that mc a minus me a is equal to or I'm sorry, we want to subtract. So then this would become positive. We're subtracting it because they're both moving along the same line, like we're saying. So ME, so MCA plus MCE, right, is equal to G, and then we're subtracting it. So we have this, right? And then these two cancel out. That. And we're left with MCAE plus that is equal to MCG plus E. This should be a minus over here. Yeah. Okay. And we have that, and now we solve for A. So we get ME minus MC over the sum times G. This is our acceleration. Right? And this comes out to be now this is if we were falling down, right? So we would experience, so if this line was cut, our acceleration downward would be a fraction, about less than a tenth of the acceleration due to gravity. Right? Now, if we were standing inside the elevator, right, and we were released, what would happen is that we would accelerate at this acceleration, which would mean that our normal force, the force that keeps us upright in the elevator, would be less, because now we're experiencing an acceleration. So if we're standing in an elevator, right, and it's moving downwards with this acceleration of 0.6, right, the force that we would feel our weight to be would be less than what we would normally feel, right? Because the force that we normally feel on the legs is due to the normal force. If there's no normal force, we'd be in free fall. And if there's no other force besides gravity, we wouldn't feel like there's any force on us. When we feel a force, that's actually the negation of these two forces, because if it wasn't, we would just accelerate and we wouldn't notice it. So in this case, right, we would have this acceleration, which we set it equal to this, and then we would take Fg minus this and we find that Fn, the normal force, will be less than normal than what we normally feel if we're standing on the earth, right, by Ma. And actually, I do this, well, I used to do this. So if you're in an elevator and you're reaching the top floor, and as you're reaching it, you notice the elevator is slowing down. And as long as your weights are just right, not to cause the elevator to collapse, and you jump right when it's slowing down, you could jump much higher. And it's kind of like a cool feeling. And then as you're coming down and you deaccelerate at the bottom, we're applying a larger than normal force. And if you jump then, you can hardly jump at all because you're experiencing an acceleration or a normal force that's larger than just gravity, because we're slowing down at that case, in that case. Okay. Any questions on this?
Wait, so when we have a higher acceleration, we downwards, we're heavier? That's what you're trying to say?
No,
or?
we're lighter. It feels like
we're lighter. Okay,
okay. There's less normal force. So if you look at a normal force equation right over here, it's probably hard to see a little bit. This is subtraction of our acceleration.
Okay.
Right, because our weight that we feel, it's actually the normal force canceling out with the gravitational force, and it's kind of like smushing our skin together in so many words. And we have pressure sensors that sense that. Once we're in an elevator that's falling with us, where part of that acceleration downwards is coming from gravity, right? So that means that the normal force is not negating all of the gravitational force. So that normal force is less. So that means there's less pressure on between the rest of our feet, the soles of our feet, and the rest of our body. We feel like we're lighter. So even though we still feel the same, even though we still have the same force of gravity acting on us, we feel weight or like we're less weight or weightless if we're falling in free fall, because there's nothing to counteract that force. Right? And this is the idea with astronauts in space. So astronauts in space, right? They circled the globe. What actually is happening is that you could consider them in free fall. They're always falling, but they're moving so fast in this direction. It's like a parabolic arc. Actually, this is really cool. This is a good. So this is actually a thought experiment when we're first thinking about getting from off of the Earth, right? So when we throw an object, right, it's a parabolic arc like this, right? If we throw it far enough, it'll come down here, right? And then if we throw it even harder, what would happen is that it'll keep trying to fall, but there won't be any earth for it to fall into. So what happens is that it keeps rotating around like that. Now this is a simplistic view of it. We'll go into this in more details later, but this was the thought process for putting people in orbit. That I forgot which scientist thought of this first, but this idea of constantly falling around the Earth, and the fact that you're going so fast, you miss solid ground basically, right? And you just keep rotating around. And in this case, you're free falling. You're constantly free falling, but because there's no force to stop you from falling, you don't feel the force due to gravity. It's just totally as an acceleration. This is why, when you're in orbit, you feel weightless. It's not that you're not feeling the force due to gravity. You're feeling the force due to gravity very close to what we have on Earth. It's just that there's no other force to cancel this force due to gravity, because we're always going around the planet. Right? So this is a good intuitive way to look at forces. Right? Now, so I just want to talk briefly about mechanical advantage. It is quite interesting. So we use this all the time in lifting objects and in cranes, right? So there's a way to reduce the force, right? So let's say if we have a crane on top of a building. Yada, 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 right? This is a crane on top of the building, right? And we have a person pulling the rope at the top, right? FT, right? And the way the rope is set up, it's set up so that there's a two-pulley system. One end of the rope is tied over here. The other, then it's connected by a pulley. This pulley is attached to the object that we're lifting, a piano, let's say. And then the person is pulling up top, right? So let's say the piano has a force of mg. How much does Ft have to be to lift up this object? Let me ask you. What do you think?
mg.
Mg, right? We have to apply the same tension to lift up this object, right? Now, let's see what happens. So let's see the force diagram on this, right? Now, remember that, so the tension throughout this whole string is the same, right? So so the tension force over here, right, is Ft. What is the tension force over here? Ft, right? What is the tension force on this side? Right over here. This is also Ft, right? Now let's draw a free body diagram of this. So let's say we have mg, right? And then we have 1 Ft, right? But there's two places that this rope is connected to this pulley, right? One on this side and one on that side. So what does that tell you? Is there any other forces involved in this problem? There would be another Ft over here. I'll draw it right over here. So there's actually two Ft's. See? So that means if we have two forces going upwards, right? If we write out the force equation, is equal to 1 Ft plus 2 Ft's minus mg. Now, if we're not moving anything, we set this to 0 to keep it from falling. We would end up having Ft is equal to 1/2 mg. So we actually only need to apply half the force to lift up this object, to hold this object upright or in the sky, right? That's amazing, right? It's almost like you're getting something for nothing by setting up this system, right? But we don't get this for nothing, right? And we'll see why. If anybody can think of a way of the reason why we get this, we have to account for this. We don't get this free. Please tell me. Now, just think about the distances that we have to move the objects in this scenario, and If you come up with the answer, let me know.
Angles.
Yeah.
Does it have to do with the angles?
No, it doesn't. I'll leave that as an open question. We actually don't get this force for free. It does take into account somewhere. And you haven't learned the topic yet. It has to do with energy and work. We'll get to it. So the fact that we have we're using this pulley system, we get double the force. We could even extend this and do a triple pulley system, and where we have the rope connected to it in 3 places.
Wait, is it the conservation of energy?
Yeah.
If it's released with less, it's saved more. Like for example, the loss of energy. For example, if a car speeds faster, it loses more energy compared to fewer slowly accelerate.
Oh no. That's because of other stuff with the car, the dynamics of the car itself.
No, but like the more energy that's put out, the more is it's lost faster.
That's because of the speed. So the faster the car goes, the more wind resistance you have, and you lose energy that way. It doesn't have to do with that. So this, you don't assume that you neglect any air resistance. So think about how much distance I have to move when I'm up here compared to how this moves. That's the hint. But I want to do one more problem, and then we'll call it a day. And this is chapter 4. And then I'll make this homework due Sunday. Okay. Okay. So now let's look at an incline, a box going down an inclined plane. So let's assume that we have this box on an inclined plane, right? It's at an angle, right? So now there's a force of gravity going downwards, right? What other forces are there in this situation? Is there a normal force? Yes, there is. And where is this normal force? Which direction is this normal force in? Is it the same direct? Is it upwards with gravity?
Isn't it the same as the slant that it's on?
Yes, right. The normal force, how we define the normal force, it's always perpendicular to the surface that it's coming from. So if you look at the surface, it's making an angle theta with gravity, which we'll show in a minute, so that the normal force is in this direction, right? So this normal force is in this direction, right? Now let's figure out the accelerations. Let's figure out the acceleration. Or let's determine what the normal force is on this object, right? Let's do that first, and then we'll do the acceleration. So A, F, N, B, A. What is the acceleration of the box? Right. And then evaluate and theta is equal to 30. All right? So let's figure this out. Okay, so how do we calculate this, right? We need to break this down into components, right? So we need to first figure out how do we want our axes set up? Do we want our axes set up this way, up and down, to go along with the gravitational force? Or do we want to, or is there another axis, or is there another coordinate system that's more convenient?
Yeah, make the y-axis what is it, the Fn, and then the x-axis is the ramp.
Okay, so you're saying like this, right?
Yes, sir.
What's the benefits of it like this as compared to, something that we normally treat? What's the benefits of this?
We're not gonna have to split them into components. Well,
We're not gonna have to
at
split
least,
the Fn into components, right?
yeah.
Yeah, that would make that easier. Well, we're gonna have to do the mg into components. So one of these we're gonna have to break up into components, correct? In the end, for part A, we're looking for Fn, right? So maybe for part A, it's best to do it like this. But what about part B? Where would the acceleration be if we had any?
Sorry, what'd you say?
Which direction would the acceleration be if there is an acceleration? We can assume that there is, but if there is, which direction would that be in? So if a box is sliding down the ramp, which direction is the acceleration? Down the ramp, right? So
I thought it was a trick question.
yes, it was. I'm sorry. So it's down the ramp, right? And a lot of these questions, it's hard to figure out what the answer is, but once you know the answer, it's like, oh, that's so obvious that I should have thought of it myself. So even though a problem may seem hard, there always seems to be some approximation or some way you can manipulate it to make it simple or simpler so that we can understand it. So the acceleration is only along this direction, right? There's no, the normal force is this, I'll call it a reactionary force to gravity, right? There's no random normal force. So we know that it's not moving upwards, it can only slide in this direction. So it's nice to have the acceleration in that direction. And that's why we usually set up the coordinate system this way. Also, in this problem, we're solving Fn in the y direction, but it's mainly so that the acceleration is in only one direction. It makes our lives easier. So let's figure out what Fn is. So Fn is all along the y direction, right? So we'll call that in the y is equal to ma. We know that the acceleration is 0 along this direction. We only have a force going in the negative y and also partly in the x, that's mg, and then Fn is only in the y. So now we have Fn, right? And then part of mg is also in this direction. So let's break it down. So this is our y-axis, right? That's our y. So our component is this. Our components are this, right? And if we look at the angle, we're given this angle to the horizontal. What does this angle represent? So as we move, does it represent, so if we look at this, let me draw this up a little bit better. So we have this box, right? It's actually going down that way, right? I'm just drawing it sideways. So that I'm just making the axis straight for us, right? So our gravity vector is over here, and our box is this way. Right? Does this theta represent the angle to the x-axis or the angle to the y-axis? What does this theta represent? And this. Okay, so we're lifting this up like this. So imagine, the way I always look at it, this is very intuitive. So I imagine that this box is on a plane. And then as I lift it up, which angle is increasing and which angle is decreasing? As I lift it up, I imagine this vertical vector just kind of rotating around. So it starts up, down, and then as I increase this angle, it's going more towards the x-axis. So as I increase this angle increases, and this one decreases. So we're really looking at the angle to the y-axis. Does everybody see that? We're looking at this angle over here. That's the angle that mg makes to these axes because of this plane, right? Does everybody see that? As I rotate it up, it's actually the angle to the y-axis that represents this angle. And then you can explain this by looking at this. So this angle, if I draw two perpendicular lines in our conventional horizontal and vertical direction, we could see that this angle and this angle are vertex angles to each other, right? They share a common vertex. Right, this is the straight line. This is, remember, mg is vertical. We continue that, it's that way. And Fn is along the plane of the angle, and we can see that this is actually the angle. So we have that. So so if we want to find the y component to this, right? Which direction, what cosine or sine do we want to use for the y component in this case? Do we want to use cosine or sine of this angle? So now we're given this angle. The angle next to the y-axis.
Sine.
Yes. Oh no. So if we want to find the y component or this vertical component, we would need to use cosine because this is the angle with respect to the y-axis. You see that? Right. So we would use cosine theta in this case, right? And it just has to do with the fact that the way this inclined plane translates the angle into this direction. If you don't believe me, work it out at home and just use some parallel, some triangle equalities, and you'll see that these two are equal to each other, right? So here, the y is now cosine, and then sine is now for x. So this is the y direction, and then in the x, we have ax, and then it's just the x component of mg. So it would be mg sine theta. This is the positive direction. We can see mg, the component of mg is along the positive direction this way. And we could set it up like that. There's a bunch of questions. Yep, okay. So now we have this. So let's find the normal force for A. Well, the normal force is just equal to this. You give me the mass of it and the angle of the incline, I can calculate the normal force now, right? I just solved this. This is 0, brought it to the other side. And then for B, the acceleration, right? The acceleration is, we know the acceleration is in the x direction, right? We know that this is the case. And then AX is equal to solve for AX. And if you look, that these two m's divide out on either side, right? And we're left with g sine theta. So the acceleration down this ramp is just related to g sine theta. So no matter what mass you have over here, it will fall at the same, it would slide down this incline at the same rate, assuming that there's no friction, right? The same thing as free fall. You have two objects and you neglect friction, they'll fall at the same rate. It's just that here we're going down an inclined plane, so the acceleration is less because part of the force is canceled out by the normal force, right? And if you want to look at the rest of this problem, when they plug in the numbers, please do. But it ends up coming out to be, if you use these numbers, you get Fn is equal to 85 newtons, and then A is equal to 4.5 meters per second. So it's going down halfway, about half the, it's accelerating at about half the rate as gravity does, if it's in free fall. So, and that's it for chapter 5. I'm going to try to, so I'll have this homework due Sunday, and then the quiz will be due Monday. And I'm going to start posting, I'm going to try to post some videos for chapter 5 over the weekend to make up for Tuesday. It might not be all at once, but we'll spread it out over time. Huh?
Could you give us a couple extra, like just a extra day on the homework maybe, given that there wasn't a lecture on Tuesday?
Yeah, that's fine. I'll make it due Monday. And then I want to do the quiz the day after, so you don't rush and do it all at once. I think it's good to sleep on it. So I want to go back to having, I want to do where the homework is due a day earlier than the quizzes. So I'll make the quiz due Tuesday and the homework due Monday. Sounds good?
Okay, thank you.
Yep, no problem.
All right, Professor, enjoy your day.
You too, take care.
OMR, I think you said it's on the 2nd July. The test is on the 2nd July, Professor?
Yes, tentatively it's on the 2nd of July.
Okay.
Well, most likely we'll stick to it, but I don't want to set it in stone if we're not up to that material or whatnot. So.
Got it. Thank you.
Yeah, you're welcome. Take care, guys. Have a good weekend.
Professor?
You too.
Before I leave, I want to what's called for mastering. I'm not sure how to get upgrade to full access, because I got the access code, but like I've been trying to, and I can't see the setting where I can change it.
Oh no, you have to go to it's a different master in physics. You can't upgrade it from your account. You have to, you'll end up signing up for a different one. So just go to remember how we went through it together. Is this Jediah or Samarin? How do you pronounce the name? I'm sorry. How do you pronounce your name?
Samaritan.
Samaritan. Yes. Does that mean a good neighbor? I guess.
No, it's originally Arabic, but like in my
Yes.
language they changed up the letters a little bit.
What does it mean in Arabic?
Basically fruit of religion.
Fruit of religion. Okay. Nice. It has to have some relation to the English word of Samaritan somehow.
It might.
I mean, I guess being kind to your neighbor is like the root of religion. But anyway, or fruit of religion, right? We should say that.
Yeah.
It's the fruit of religion is kindness or something like that. Okay, so for master in physics, you will have to sign up for the account. So remember how we did it last time we went to that web page, and you'll have to type in the access code for that I gave in the syllabus.
Mm-hmm.
And then just sign up for the new account, and then I'll transfer over your grades, your initial grades, okay?
I have to make a new account?
Yes, you have to sign up for that new account. Or sign up for the new course. You could use the same account, but it's going to be a completely different course. Well, not it'll be, that different course code.
So what? Wait. When I go to join a course, was it in the email that you? I think it was an email, right?
Yeah, just go. Yeah. You could also email that woman, our contact with Master in Physics.
Pearson representative?
Yeah, that Pearson representative. Do you have her email? I forwarded the email that she provided with the course, with the details on the temporary course. So